So we're going to do phase analysis, just kind of some 101 on this. I also like to do a little history perspective as well, as right, we are in a field that is sort of rapidly changing in the last couple decades. Live product walkthrough to show you some things we have actually right now integrated into our platform with phase, some applied use case. And lastly, we'll have some time for Q&A and some additional kind of follow-up steps. So awesome. Let's get started. Okay. So I will caution here if we do have any more seasoned vibration guys that have seen any of this 70s and 80s equipment. This is me looking through Google. So this is definitely the least experienced part for me here. But like I said, I think it's really just a good kind of piece of perspective when we're talking about the future of where this industry is going. So vibration analysis itself has been around since the early 40s. It was pretty common in certain applications in the 60s for aerospace or very expensive, applications that really spending a very large chunk of money on vibration analysis made sense, as it was still very experimental at that time. Around the late 70s is when they started seeing what I would call like more applicable to what we do, reliability-based techniques and tools. So here is just one. I thought this is just a cool picture from the late 70s here of the HP 3582A. This is one of the first what they call portable units. I was not able to find an original price, unfortunately. I was really hoping I could find that, but that'd be fun. Some perspective here, it weighed 54 pounds. It was definitely not cheap. So think this was more applied to things like large vertical pumps, things that, are pumping out thousands, if not millions of gallons of water, these kinds of things. In this case, we do have the technology here for our vibration. The nerds on the call, they did have the ability to track harmonics and things that we kind of consider typical to diagnostics today. But there's definitely a lot of noise in the signal, a lot of setup. And again, it was not necessarily convenient to use. Reliability guys did not get any experience with this. So that was kind of the early days. Moving to the 80s and the 90s, this is when we really started to see vibration become a part of reliability, looking into that condition-based, route-based, checking in on things over periods of time, using that data to make more informed decisions in the future. So this is really when that kind of came to be. So it started with the single channel route-based portable analyzers. These had the ability to take phase. You had to use what was called a tachometer, which does have some time and difficulty getting that set up. Like it's pretty straightforward, but you have to turn the machine off, these kinds of things. So it was a possibility. But again, even just taking regular vibration this easily was pretty new. And then when we got more into the 90s, we're looking at the 2-channel phase, which we're going to be talking about. This is more of what we're going to be using in our Halo sensors going forward. But the idea with the 2-channel is it's much easier to use. You do not need to use a tachometer in those cases for a phase reference. So you can truly just kind of set these up like sensors installed on the machine. It's non-invasive, right? Doesn't require a lot of extra effort there. So this is just some basics here. Obviously, there are lots of other technologies, but as far as for this condition-based kind of space, to me, then the next chunk is sort of the 2010s. So, looking at how can we start using this stuff wirelessly? How can we not have all of our guys either be getting experience as a vibration analyst in maybe one field, right? Maybe they're one guy at one particular plant for 20 years and they're very good at vibration there, but trying to get industry experience otherwise could be very challenging. Finding people that have robust experience like that can also be very challenging. So this was sort of the play here. How do we get this sort of wireless? We're going to get a lot more data, 24/7 remote monitoring, right? We're all familiar with this idea. The big challenge here as far as phase and really what we have spent the most of the time as we've been developing this capability is there's sort of two needs here with phase. We need to be able to perfectly time sync the sensors that we are trying to take these phase readings, which is just very difficult to do from a hardware perspective. The second piece of it is from a battery life perspective. So yes, as much as I think it's awesome and very useful to have phase analysis, if it results in, customers with thousands of sensors having to replace those batteries every 6 months instead of every 2 to 3 years, like they're expecting, right? That's not really a good solution. So this has been sort of the biggest hurdle, at least for us here, and we have been able to overcome that. So just moving now into, a comparison sort of how things were done previously to sort of where we're at now. So just trying to give some pros and cons with this. A lot of these, for people that are familiar with this remote condition-based monitoring, a lot of these are not necessarily unique to phase. So, the pros doing route-based type of work, you get that visual and tactical context. For someone like myself, being able to walk around a machine to really get a sense of what's going on. Maybe there's loose bolts, maybe they shim one side of the motor too much, right? These kinds of things give you all kinds of additional context that you're obviously not going to have in that remote based experience. Additionally, being able to do adaptive phase testing. So there are different techniques you can use. For example, if you have multi-tier structure to check for where the actual looseness is, this involves moving the sensor several different places. Obviously, this is something we really can't do in that remote context. The last piece here is going to be that sensor precision. So just to put it bluntly, if I'm taking my own readings, I can rest assured that I have the most confidence in my own position of those sensors, making sure they're in the best location to take those phase readings. The downsides of this, again, very similar to condition-based monitoring, just in general, what we call the snapshot trap. So right, you're really only getting this phase reading for maybe one period of operation, one speed, whatever the case is, depending on how your system is set up, if you can take phase at all. And some of these things are significantly affected by how the machine is operating, what speeds it's at. For example, unbalance will significantly increase as the speed increases. So really just being able to not only take phase readings, but take those under all the conditions that are necessary can be very challenging. Obviously, from just pure logistics, safety, and access to some of the machines, especially the ones that we monitor, right? We're not in the early 2010s anymore. Most of our customers are really looking to have these sensors in difficult places to put them, right? Because they don't want to be doing repair and maintenance work in cases that they don't need to and that are very challenging to access to take vibration readings, let alone do maintenance. And obviously, labor intensive. You need someone that's intelligent as far as the phase intelligence, knowing how to take this, have experience, what to kind of do with those readings over time, et cetera. So just specific skills. So then on the condition-based, remote side of this, right, the pros of this, large data set context. So what I mean by this, and I'm going to show a good example of this later, there are many cases in which phase is not going to be a perfect solution. We're going to go through the cases that it is, excuse me. But there are also cases that it's not going to give you a clear black and white answer. However, with the ability to trend vibration data, for us, it's typically once an hour, if not more. Vibration, temperature, for us, magnetic data has us have the ability to detect speed changes over time, so operational conditions. We can also take in additional data from the customer, think, process parameters, those sorts of things. So having this data as well as another piece of that puzzle, even if in cases it doesn't give us a black and white answer, is something that we can lean on in the future. And this is not something you can kind of do in that traditional route-based sense. That second part I mentioned here, that speed load correlation, this is huge, especially for Augury. We have customers that very much run their machines all over the place, speed-wise, conditions-wise, maybe different products, these kinds of things. We're going to be opening this phase capability to not just sort of the standard machines that vibration analysts are expecting to see these on, fans, pumps, blowers, things like that, those more simple machines. We're going to be employing this to every sensor that we have that has this capability. So even those more complex machines, again, we're going to be able to use this as another piece of that information. Last here is that historic analysis context. So being able to, again, cross-reference over time if we had similar kind of phase changes with the vibration in the past. So really being able to pinpoint specific solutions to each customer with our platform, we're able to then also time sync that. So for example, if you had a repair last year, we see some kind of odd phase shift as well as a very large change in the vibration, right? We can correlate that right to that repair, reference that back, specific things that the customer did at that point. So really try to continue to keep it custom to that specific scenario. On the con side, again, very, very much the same for just remote based in general. We do have sensor mounting constraints. So there are certain types of phase analysis, I would say the less common needed, but these, we can't move the sensors, right? We put them in the best place they can be to catch, the common faults. So these are where these are going to stay. And then like this last piece here, again, right, we rely on the customers in some cases to put these sensors back on the machines after repairs, things like that, right? So that's obviously something we need to work with the customer to try to keep consistency, at least with the physical location, right? If we're several inches from a bearing and those kinds of things, again, this is just kind of natural to all remote-based condition monitoring. But just kind of wanted to show that here as far as what we see in the pros and cons. Okay, so what does this mean for your day to day? Like, what does phase do for you? Really, the idea behind this is it can be a diagnostic tiebreaker. So there are certain types of mechanical faults that have a very, very similar vibration signature, even in very simple applications. Like I mentioned, we're going to see phase on more complicated machines here at Augury, but even those simple ones, there are multiple types of faults that have very similar looking vibration signatures, which makes it hard to diagnose those, right? So things like unbalance, misalignment, looseness. With phase, we can easily differentiate these things. So, right, getting more accurate on these very common types of those faults is huge. The second part here is repair quality validation. So again, let's think of a scenario like a misalignment. So today we can see a very large change in the vibration. Let's say the vibration analyst does the correct thing, diagnoses misalignment, and that gets corrected. Even if the vibration is lower, we will still be able to see if there are signs of that earlier misalignment with the phase. It's going to have a particular look to it, a particular shape to it that we're going to be expecting. So we'll be able to kind of validate right after those repair events, which can be very challenging, right? If we have lower vibration right after an event, we do want to give quick feedback to the customer, but being able to confirm the phase here is a huge differentiator. And like I mentioned, this last piece, that historical context. So we will have phase available on some very complex machine types that we won't necessarily expect that we're going to see all the very traditional types of phase faults here. But having the ability to track this with all those other parameters I mentioned is going to be able to make us make more informed decisions as we go, as we collect more history on those machines. So what is phase analysis, right? I'm talking kind of hyperbolically about it. For us, I think the simplest way to think about phase analysis is how it relates to vibration. So vibration, think of like a movie, something on a movie screen, and we're going to show an animation here shortly. But vibration is going to tell you the intensity something shakes, so the distance it moves, and at what frequency. So what speed? So we get a distance and a speed as far as the visual. Phase analysis is going to tell you how multiple things relate to each other. So for example, the idea of if you're listening to a band perform live, it's pretty easy to tell if the singer is very much out of key, right? Somebody's pretty used to hearing that in their ears. We've all heard American Idol. The idea here with phase analysis, though, is it can be much trickier to, for example, to tell which band member, for example, may be playing out of time with the others. So this is what the phase analysis gets us. It's not only telling us, yes, we have vibration patterns, and this is kind of the level of the severity, but how does this relate from component to component across the machine? So we're going to show an animation here. Okay, so from our animation here, this is what we call like a basic spring mass example. The idea here is the vibration is that distance that this is moving up and down. The speed at which this happens, we call the frequency, right? So this is two of the three pieces here. And then that last piece is how these relate to each other. So in this case, these would be called in phase, right? They're perfectly moving up and down together. If they moved in opposite direction, we would call that out of phase, 180 degrees out of phase. So this is essentially those three components you need to a visual. So like I mentioned, this is kind of used to route vibration, but the principal idea is so your analyst can visualize how that vibration is affecting that particular machine with higher resolution there.